All right. Hi, everybody. Welcome to today's AP Physics 1 5able live stream. Today is all about open Q&A, so pretty much it's going to be whatever questions you guys have, we're going to go through and answer. So before we jump into questions, let me just give you a quick overview again, because I'm sure you guys are all aware of this. It's Wednesday, which means it's Science Day. We've got a Physics 1 stream at 7 o'clock tonight, focusing on rotational forces, angular momentum, that sort of stuff like that. So come check that out as well. Yeah, next Wednesday, we're going over free response questions from last year's AP exam. Anything that's covered on this year's, we'll go over. And then if we have extra time, hit the other ones. And then more momentum stuff next Wednesday night as well. If you guys have questions at any time, please throw up in the chat or use that Ask a Question button, and I will do my best to answer them. All right, so that being said, we've got our first question here. So let me switch over to my paper. Maybe that'll work. Hopefully that'll work. We'll find out in a second. Chrome tab, paper, go. Go, paper, go. All right, so our first question is, we have a car going over a hill. How do we compare the weight and the normal force at various different points on there? All right, so let's start with my terrible drawing of a hill. Okay, we're going to exaggerate that a little bit, but there's my hill right there. And we're going to start with a car being basically three different points on here. We're going to look at point A. We're going to look at point B, which is the top of the hill. And then finally, point C going down the hill on there. Okay, and a banked curve. Yep, I can work on a banked curve one too. Sure, they kind of go together. So, all right, so let's just look at simple sort of stuff. I'm assuming there's no friction at all on this curve. I'm assuming that the car is just coasting, so there's no force from the engine or from the wheels or anything like that. It's just a plain car sliding over this thing. I'm also going to assume that it remains in contact at all these points and doesn't fly off the top. All right, so that means there's only two forces acting on our car at any given point in this situation. We have gravity, we have normal force. And for some of these, it's pretty straightforward. For example, B, gravity goes straight down, and our normal force goes straight up. Now remember, normal force is always perpendicular to the surface. So at point C, it's going off in this direction, and point A, it's going off in that direction, because again, we need to have this perpendicular relationship to the surface. So again, if I was to draw a tangent line in there, for example, that gives me a 90, that gives me a 90, and that gives me a 90. So we have all these. So at the highest point, it's not centripetally accelerating. Well, it is in there. Notice I haven't said which one's equal or not yet, John, in there. There must be a centripetal force all the way throughout this problem, which means there must be some portion of this force, our net force, our overall force, pointing towards the center of our circle. And again, drawn badly in black, that's kind of what we're looking at here. Which means, since my net force has to be pointing towards the center at each of these, we have a discrepancy between the size and the direction of those forces. Okay, so let me finish drawing these in here for a second and going in there. And that is kind of the gist of what's going on. At point A, obviously gravity and the normal force are not going to cancel each other out. There needs to be a component of that pointing towards the center. And if we wanted to draw that in a little bit clearer here, we could say that some part of the normal force must be pointing up and some part of it must be going, actually, hold on. Let's not do it with the normal force. Let's do it with gravity, because gravity is the one that's going to point towards the center. So some part of gravity must be going down like this, and some part must be that way. Those parts are equal. And then the other part, this unbalanced part, is our centripetal force going through there. Okay. So that's point A. Point B is a little bit clearer. We need to have our centripetal force be equal to the weight minus the normal force. So gravity, again, is bigger. They're not equal in magnitude here because we need to be accelerating through here. Now, if you can imagine, if we were at a place where the normal force didn't have to be there, if it was zero, then you'd feel weightlessness. You would feel nothing pushing up on you. And that's where you're going to get that idea of weightlessness, is when the normal force approaches zero, we are weightless. And then basically the same thing that happens at A happens at C, where you've got some component of the weight actually pulling towards the center of the circle. But mg cos theta doesn't point directly towards the center of the circle at point A, right? Right. Really what you would do, and again, this is not something that I'm expecting you to have to do on an AP exam. What I would have my kids do is, for example, we would take this wonderful section here. I'm going to blow it up a little bit. So I've got the curve, I've got the gravity, I've got the normal force. I would almost set up my system so that I have my axes looking like that, and then redefine those parts. So you would basically choose your angles and find your components. Actually, hold on, I didn't draw that right. Can I drag you? Can I drag you? That's better. Drag it so that we actually get one pointing towards the center of the circle in that case. So then you'd find components of the normal force and components of gravity, do an F equals ma for both of them, and then whatever's left there. So it's double components, essentially, is what you're doing there. This is also slightly more complicated because we would actually be slowing down a little bit there. So some part of the gravity is actually doing work on it as well, and that sort of thing. Most of the, yeah, that's what I would do, is just basically set it up so one of the axes always points towards the center, and then find your components from there, because we have complete freedom on which axes we get to choose. So let's make it so we have one that the horizontal axis is pointing directly towards the center of the circle, and then we find our components from there and go from there. Okay, cool. All right, next chunk, banked curve. All right, so banked curves are one of these things that comes up from time to time. Let me see if I can find an example of one on here. Forces, where you have kind of like what we just did, where it's one part of the force is pointing towards the center of the circle, one part is not. So let me grab a little picture of one here. Okay, so this is an old one, but it'll work. Copy. Ignore the text on the bottom because that text is not what I need right now. Paste. Okay, so we've got this wonderful little truck going around a curve. Ignoring the text because that's not important. Okay, and this truck, for example, is going a perfect circle around there. So top down, we'd see a very nice circle, uniform circular motion, all that wonderful stuff happening here. What we can say then is there must be some force pointing towards the center of the circle. I wonder what force that could be. Well, there's only one force that can actually do it. And this is one that if you guys have been out driving, you may have experienced a little bit. The force here is friction. Friction's got to be the only possible force that can point towards the center of the circle. And in this case, we're going to have gravity help on a little bit as well. Or sorry, the normal force help on a little bit as well. Let me just find my example of this because I wasn't planning on a banked curve. Banked curves aren't ones that normally come up on the AP exam either. So, but this is at least something that could be asked. Springs, forces, tensioning, strain. Okay, we're getting close. Where's my question? No, that's energy. That's not the right ones. Circular motion. There we go. Okay. All right, I'm back. Okay, so with this question, we're going to have our box, basically our object basically be sitting there. We got two forces essentially acting on it. We can assume there's friction or not. For the sake of ease, let's assume there's no friction. And you've got this normal force heading up that way and gravity going straight down. If you had friction, friction is actually going to try to stop this thing from moving, which means it will be pointing, let's see, tries to stop it from moving. If there was no friction, we keep going a straight line, so you'd have friction going downwards as well if there was friction. But I'm going to ignore it because I want a simpler problem. Okay, so this thing going around the corner, basically we're going to be asking a question like, how fast can we go and still make this corner on there? So we're going to be given something like this on there. They may be really nice and tell us the angle of the curve. So say that's a certain angle theta. That's wonderful too. And basically, we got to remember that, hey, some part of this must point towards the center. So in order to go around a circle, a force must be pointing towards the center. So let's see if we can make up some axes to let this happen. For my sake, I really like the idea of my axes being kind of like that, where I have my y-axis going upwards and my x-axis points directly towards the center of the circle. I also don't need to worry about gravity contributing at all here either, because gravity is just going to be going straight down. Okay. What this means is that the normal force has to do two jobs. There must be some vertical part of the normal force canceling out the weight, and there must be some horizontal force or horizontal component of the normal force that causes us to accelerate. That is my centripetal force right there. So how do we solve this? Well, let's look at our 2 Newton's laws equation here. All the vertical forces should cancel out. We're not going to go flying up in the air or crashing to the ground. That'd be good to know. We also know that we must have our horizontal forces must be equal to MA, because we're going in a circle. That's also MV squared over R. And now I didn't make up R's for this problem, so we're just going to leave it in terms of variables, probably because that's what you're going to see on the exam as well on there. So from this, we've got our z, which means I didn't do the right angle, but that's okay. It'll be fine. It'll all work out in the right end. Boy, can you tell I haven't done banked curves in a while? Where's my banked curve problem? There you go. Good. Yeah, okay. So we've got our theta. That's not the right theta. Z. Oh, how I hate geometry. That's my theta. So this will be Fn cos theta equals mv squared over r, and this would be Fn sine theta equals mg. I may have the trig terms backwards on there. I just got to think about it. Similar triangles, 90-degree angle. It is the bottom one. Cos, sine, get rid of that. It is that bottom angle. Okay, there we go. So that means mg over cos theta equals my normal force. And then we plug this in here. Mg sine theta over cos theta equals mv squared over r. We then can simplify a little bit. We can drop some m's, so the mass of the object doesn't matter. That's kind of useful to know, that if you're designing a curve for civil engineering or something like that, you can design it for pretty much any object you want to, and we're going to be okay because the m's all cross out. that means that at the end, v is going to be the square root of gr tan theta. And then that will be the maximum speed that you can go around that corner in. Assuming no friction or anything like that. Friction would actually help with this. It helped grip you and pull the vehicle around the curve. So if you're designing it, this would be the best case scenario, or sorry, the worst case scenario where the road is so slick there is no friction at all. Can you still make it around there with just the bank of the curve working? All right, that makes sense? Cool. All right, what's next? Stick with forces. Work. Okay, so work is one of those wonderfully weird things. Yeah, essentially, work is the change in energy. But what's wonderful about energy, and I tell my kids this, energy is a completely made-up idea that works great because it explains what's going on around us. But it is tough for us to physically grasp what energy is because you can't hold energy. You can't say this has energy. All you can do is say that energy gets transferred from one thing to another. So this has more energy or this has less energy than something else. Work at its most basic definition is the change in total energy. So now this, John, might be mechanical. It might not be. Remember, mechanical energy is just kinetic and potential going on there. Whereas work could also change thermal energy or sound energy or electromagnetic energy, that sort of thing. So for example, if I am using a drill to hang a shelf or something like that, the drill has energy flowing into it from the battery. It's taking electrical energy and converting it to mechanical, which then in the end with that drill bit gets converted into thermal because the sound and the heating up the wall and stuff like that goes on in there. But yeah, essentially work is just adding or removing energy. In general, negative work means you're removing energy and positive work means you're adding energy to it. So yeah, it really depends on the situation. It could be delta ET, but let's say, for example, it's a flat surface and I'm just pushing a box. So I've got this force going along a certain distance on there. There's no friction or anything like that. The work done here, yes, it does change the total energy, but reality is just the kinetic energy because that's just the way it's going to be. It's simpler for us to say instead of doing, okay, is this work? Is it changing potential? No. Is it changing thermal? No. Is it changing magnetic? No. Okay, it's just kinetic then, so we'll just leave it as that. So it really depends on your situation. It's never wrong to write this. Okay? Sometimes it's right to say that, but also if you're doing this completely vertically, just lifting this up, and I go from not moving here to not moving at that new height, this would be delta potential because we're not changing the kinetic at all. Okay, yeah, so dropping a book, gravity does positive work on the book, but doesn't change the total energy, which seems weird. Okay, this goes back to our idea of systems. So if we're looking at our book falling, right, it's got this force gravity pulling down on it. If we say the system is just the book, okay, that book has an unbalanced outside force acting on it, gravity. The work there changes the kinetic energy of the book, and therefore the total energy goes up. Remember, if we don't include the Earth at all, if the Earth underneath it, that's a terrible way of spelling Earth. If the Earth underneath it doesn't exist, right, is not included in our system, we don't get to talk about potential energy because we have no height to reference it from. So if we're just looking at the book, we say the total energy of the book increases. True. Okay. If we look at the book and the earth, which is what we normally do, we say, okay, now that book starts a certain height from the earth. It has potential energy. As that falls, gravity still pulls on it. We still have this force, but this force is now an internal force. It is still a force, but it's caused by something inside my system. That force no longer does work because work requires an external force or a net force or an outside force, whatever term you want to use for it, in there. So now we can say that the total change in energy must be zero. We have potential energy going down and therefore kinetic energy going up. Both cases agree that we gained kinetic energy, right? Both cases are going to say, hey, that book's moving faster than it was before. But it just depends on how you approach the question. Are we talking about conservation of energy when we're including the Earth and saying, okay, the whole thing lost potential but gained kinetic, total doesn't change? Or are we talking about just the book? Just the book just gained kinetic energy. There must be work done. That work was done by gravity. MGHF, MGHO, delta K. I mean, yes, but no. Yes, so your first part, work equals delta KE works well when you just have one object. Absolutely, that's a great example of when you could use that. The problem with work, with your second part, saying that work would equal delta K and then do mg delta H equals delta K. This mg delta H, you don't have an H to really, hold on, if you're talking about the Earth book system, it's not, I don't want to say it's wrong because it's not wrong. Something about that just irks me, and I'm trying to figure out a way to explain it. Yes, this is exactly the same math I would do if I set up that side and say mg delta H equals 1/2 mv squared, or delta 1/2 mv squared, and then go from there. The biggest thing I would run into with this is when you're talking about work, again, it's an external force. It's an unbalanced outside force. When you start putting it into situations where that force is not an outside force anymore, the math works in this case. I can't guarantee it works in every case. And that's the big thing I'm not sure about by saying here, blanket statement, yes, that works all the time. In there. Does that make sense? Yeah, pretty much. For a closed system, I would always jump to the conservation of energy route. Closed system, conservation of energy, conservation of momentum, conservation of angular momentum. All those would be my three go-to starting points for this. If it's an open system, F equals ma, or torques equals I alpha, or something like that, would be my starting points for those systems. So open systems, I'm thinking Newton's laws. Closed systems, I'm thinking conservation laws. In there. No, this is a really good question because this sort of thing will come up, and it's a question of how you approach it and stuff like that in there. All right, next question, the classic 2 mass problem, one on the table, one hanging with a pulley at the side, but the pulley has mass. Okay, sure, let's do some rotation stuff. So we're gonna let's do the simple version first, make sure we're on par with the simple version, and then get into the bigger version on there. So our basic idea here, we're gonna have a box on a table with a pulley, and a rope passes over it, and now we've got our sort of situation here. Okay. Let's see. Yeah. Do we want to do this with forces, or do we want to do this? I guess the big question is, let's find the acceleration. I solved my own question. Let's do this with acceleration. We'll come back and hit this with energy as well there in a second. Hold on, my phone says I have a call, and it just hung up. Great. Okay, good. There we go. Problem solved. All right, so let's look at forces first here. Okay, so we're like big picture for forces, and let's say this pulley has a certain large mass, and give me a second to Google something quickly here. Let's see, is it going to tell me? I'm looking up, trying to see if there's a quick and easy moment of inertia for the pulley. I may just pick one then. I mean, this is one experimental way you could solve for this, but I don't think we're going to have an experimental problem. We're not going to have an experimental problem. Yeah, let's do 1/2 mr squared. Okay, so I will equal 1/2 mr squared, where m is the mass of the pulley, and r is the radius of that pulley. Okay, so for forces here, let's say we want to figure out the acceleration of m2. Well, that acceleration has to be the same for all the objects because they're still connected to each other. If we didn't care about the pulley, we could simply do look at the whole system. Gravity for m2 going down, m2g equals m1 plus m2a, solve for a. Simple. With the pulley, we have to really look at a couple different things here. This still has a force going down, m2g. We've got T2 going up. We've got T1 going that way. I'm assuming there's no friction on the table at all, which is why this will work. And then the pulley is going to have two forces on it as well, T1 and T2. Having the pulley be massive means we don't get to say that those tensions are equal to each other anymore. They must be different. Okay. So we still look at this. Sum of the forces equals MA. M2G minus T2 equals M2A. So that was block 2. Block 1 will have F equals MA. T1 equals M1A. And then finally, the pulley will have sum of torques equals I alpha. So basically, figuring out which tension's bigger, the question will tell you, or at least make it really obvious. In this case, I am assuming M2 is bigger than M1, which means if anything is going to happen, we're going to be rotating in a clockwise sort of direction. Simply because M2 should fall down and then go upwards. Because that pulley, if I'm looking at the pulley now, this pulley needs to rotate in a clockwise direction. That means the torque going that way must be bigger than the torque going in the opposite direction, which means that T2 needs to be bigger than T1. If they were reversed, if T1 was bigger, that suddenly means the pulley is rotating the opposite direction. We're hauling up M2 instead of dropping M2 in there. All right, from here, this basically just becomes a exercise in algebra. There are two torques on the pulley, T2R minus T1R, because as we already described, T2 needs to be the bigger torque to make this rotate in that direction, equals 1/2 MPR squared alpha. And alpha, remember, is A over R. That being said, let's do the combining part here, and we'll just throw everything together and then talk about it. So I'm going to solve this one for T2. I'm solving this one for T1. We plug them all into the rotational equation and then solve for A. So this is going to be, goodness, M2G minus M2A times R minus M1A R equals 1/2 MP R squared A over R. All of the R's disappear because every single term has one. The squared gets rid of the denominator one. So M2G minus M2A minus M1A equals 1/2 MPA. Get all my A's together. M2G equals M2A. They are all the same R's. Yeah, R is the radius of the pulley, which means that they're all the same R's in this case. I know I wrote a capital R, lowercase r in a couple spots here, but we'll just make them all capital. Yeah, in this case, all the radiuses are the same. So that means that A will equal M2G divided by M2 plus M1 plus 1/2 the mass of the pulley. And there is our acceleration of that object going down. And that's probably what, if they're going to ask you a question like this, that's probably where you're going with it. I'm trying to think of another situation. They may ask you energy for like a bar graph sort of situation, or maybe even to compare with a small pulley versus a large pulley, what's going to happen. And the big difference here is if we have massless pulley, we're going to get more acceleration because this 1/2 MP will be 0 and therefore won't make a difference in the grand scheme of things in there. Okay, but just thinking about this, if they do something like this on the exam, this could be a good way to bring in forces and rotational stuff in there. If the rope had mass or the table had friction, the acceleration would be smaller. Yeah, we would never see a situation on AP1 where the rope would actually have mass. But yes, that would play a role because your denominator would get bigger. If there was friction, you would then subtract a friction term from your force side of the equation. So you'd actually have, yeah, you'd end up with a smaller acceleration overall. But I'm going to eliminate that just so it doesn't confuse us when you go back and look at these notes later on. Okay, what's next? Let me see what I've got stored up here. Do we have to know much about sound? Not for this year. Sound is one of those units that is not covered on the AP exam. However, it's one that if you're taking this, I'm assuming you're taking this for credit, you're here for the reviews, the colleges are going to expect you to know about it. So what I'm going to expect is that if and when we get back into school this year, after the exam, your teacher will spend the chunk of time you have left covering that part. If you're looking for a quick overview, you can do a couple chunks on sound right now, if that's something you want to cover, but it's not going to be on this year's exam. Yeah, so for the this is again where it's a little weird. I'm in New York, which means I have to teach my kids both sound waves and electromagnetic waves, because that's what our Regents exam at the end of the year covers. So we do waves as a big unit, then pull out sound special. Realistically, you could do sound as just the waves in general. But basically, the waves we're going to see on this year's are going to be the simple harmonic motion thing. So the mass on a spring oscillating up and down makes the sine wave sort of graph in there. The only big thing that sound does other than this, you're still looking at waves, you're looking at compressions, expansions, that sort of stuff like that. The other stuff for sound would be like interference or music would be the two big things to do in there. So for example, if I take two waves and I put them exactly opposite each other, when they overlap, this leaves me with no sound. That's a noise canceling headphone sort of thing. That's kind of what the gist is between interference. If I make it so I have my waves and they end up being a maximum at the end of a tube, then I get a note. And then that note will depend on the length of the tube, which tells me the frequency of the wave and stuff like that in there. Those are the two big parts that AP covers for sound. That, yeah, so volume is amplitude. So that's definitely the height of the wave right there. I drew that wrong. Amplitude is not the entire wave. Amplitude is from our middle point right there. So our amplitude, and yeah, this tells us volume. Or in a bigger sense, this tells us the energy that the wave has on there. Okay, going back to the mass on a spring, the farther you stretch that spring out, the more energy you have in that spring and the wider its motion is. So yeah, that would be amplitude in there. Yeah. Okay, ooh, new question. We got impulse problem. Okay, so impulse. I guess what kind of impulse question do you want to do? That's kind of a silly question. Let's see if I can find a good. Yeah. Okay, I don't have a ton of these set up already, but let's look at this one. I'm just going to Google for an image real quick here. Those are velocity time graphs. This is the one I want. Okay, great. Grab me this picture. Copy the picture. Paste the picture in over here. Okay, so let's take this figure here and let's do some impulse stuff with it. Let's assume, I'm going to get rid of the problem 63 part here. Okay, let's assume that we are starting this with a velocity of 0. We're starting our car at rest, or our object at rest. Doesn't have to be a car. Where is it moving the fastest? So what's the maximum speed? At what time does that happen? And then what is its speed at the end? All right. So for this, there's a couple ways you could solve this problem. There is the, hey, you've got forces. We can find some forces, do some F equals ma stuff, and then go from there. Actually, let's call this, yeah, let's say this is a 1 kilogram vehicle, because that'll make it easier to do the math out. So you could find the force at any given point, do some F equals ma's, A equals delta V over T, and find the velocity from there, stuff like that. We're going to do this with impulse because impulse is a little bit easier. Remember, impulse is a force times a time, and that is the change in momentum of our object. Right? So Ft delta P, the bigger F or the bigger T gives us the bigger change. For this, force time is the area under our curves. So to do this one, we're going to have to kind of break this up into some shapes. I personally do triangles and squares, although if you guys have done and memorized area of trapezoid, that also works really well here. But what I'm going to do is let's break up this part right here. So we're going to go across. I'm thinking that looks like a good shape. That one looks like a triangle. And kind of break it into those 4 shapes right there. Right? Every single one of these is a positive force, which means we're going to be speeding up or accelerating in the positive direction all throughout that. That should all give me positive velocity. I know that at 6 seconds, we must be going the fastest, because every point up until 6 seconds, we have done a positive force on that. We've been accelerating in the positive direction. Everything after 6 seconds is all negative. That'll be taking away momentum, slowing us down. So our maximum velocity must be at 6 seconds, because that's the point where we switch from going from positive to negative. So to figure this out, let's see, 1, 2, 3, 4, 5 times 2. So this is 10. 1, 2, 3 by 4, that's 12. 1/2 of 2 times 4 is 4. 1/2 of 1 times 6 is 3. Adding all these up, that means my impulse from 0 to 6 seconds is equal to 10, 20, 26, 29 kilogram meter per second, which means that my velocity, since P equals mv, we can then say our velocity is 29 meters per second. The second thing we could do is look for the negative chunk of this and say, okay, what's going on the opposite direction? Well, again, I'm going to split this into 2 triangles and a rectangle. You could, again, do a trapezoid. Trapezoid works perfectly fine in there, not a problem at all. So this is -4, 1/2 of -4 times 1, so that's -2. -4 times 2, so that's -8. And -4 times 2, half of that, so that's -4 as well. So then my impulse from 6 to 12 must be -14, which means my total J must be 15 positive. Yeah, so I'm taking 29 plus the initial velocity. Because my mass is 1, I really don't have to worry about doing any math in there. If there was, let's say my mass was 2, I would take that delta V and divide it by 2 or stuff like that in there. But solving for delta V here in there. So that means that my total delta P, so that's 1 kilogram, delta V equals 15. Delta V must equal 15 meters per second at the end. And there is our solution to that one. All right, that makes sense? Yep, no problem. All right, what's next? We probably got time for 1, maybe 2 more topics depending here. We got 15 minutes or so. What else do you want to cover? Relative velocity, meaning what? Let me try to think here. Are we talking about object A, object B moving at different speeds? What's their velocity relative to each other? Okay, boat and water, sure. Yeah, so, yep, boat and water. Got it. Okay, so let's do the very classic boat water problem here. This could also be airplane and wind or other stuff like that. But let's say we've got a boat going down a river, and the river's velocity is 5 meters per second. And I've got my little boat here. And my boat really can do a few different things. My boat's maximum velocity that I can make is 3 meters per second. My poor little boat. Actually, let's make it 6. Let's make it so I can actually do something here. 6 meters per second is my maximum velocity for that boat. Okay, and my boat has a few different directions we can choose to go in. Right? We can choose to go upstream. If we go upstream, these two velocities are completely opposed to each other and therefore would do some canceling out. So my net velocity here, if I'm going upstream, would be 1 meter per second up. If I decided to go downstream and run with the current, so now I've got my V going down, this V is going down, my total velocity here would be 11 meters per second in the downward direction. Or I suppose if we're calling this positive, that means that down has to be negative in that case. The other two, if I go left or I go right, actually get solved the same sort of way, or the same solution for both. For both of them, all is going to change the direction a little bit. For these guys, we're going to have our velocity, I'll do the right one right now, and then we're going to have the water's velocity going downwards. And our overall velocity will therefore be a Pythagorean theorem relationship here to get our V net, or our V total or something like that there. So in this case, our net velocity will be 5 squared plus 6 squared, which is 25 plus 36. Why did I really pick bad numbers here? 161 meters per second. And then if we needed to, we can do some trig to figure out our theta and talk about which way. So this is for the right case. The left case would look exactly the same, except for the only difference would be we'd be going that way with the same square root of 61 meters per second in there. The angle would even be the same, just pointing down of left instead of down of right, or south of west instead of south of east, that sort of thing in there. Yeah. So was this the kind of chunk you wanted to cover there? Yep, no problem. Big idea here is that anytime you've got vectors, Pythagorean theorem will be your way to solve them. And if they happen to be going the same direction or opposite directions, that just simplifies to adding and subtracting in there. So not a ton of differences there. And that doesn't matter whether it's forces, displacements, velocities, momentums, accelerations, done the same way. All right. What's next? Time for one more topic. All right, we have to calculate inertia. By calculate inertia, it's possible. Will you have to derive moments of inertia based on masses and radiuses? No. So here's the example that I can give you here. If we go back to our box on table sort of thing, right, with the pulley and going over the rope to the other mass, they might be able to tell you if the acceleration is such and such with these forces and these masses, what is I for the pulley? That they could ask you to do, because that's all just algebra stuff like that, doing the same basic F equals ma and torques equals I alpha sort of stuff that you could be asked to do. Are they going to ask you to come up with the fact that I for a disk is 1/2 mr squared? No, that's an APC, not an AP1 sort of thing. So using experimental data or theoretical calculations to do it, yes. To go through and derive the ideal thing based on the shape and using calculus, no, in there. Okay. In fact, based on how the exam questions are going to come up, where they're talking about one qualitative, quantitative, one paragraph length response, I'd be surprised if you have to do anything like that. My best guess of what they're going to have you do, if they're going to ask you to do anything with inertia or moments of inertia and stuff like that, would be something like this, where, hold on, let me get rid of all this stuff here. So many undos. Okay, there we go. Something along the lines of, we've got a ball on a ramp, and we say, you know, compare a solid ball, which is 2/3 mr squared, to a disk, which is 1/2 mr squared, to a hoop, which is mr squared. Which one reaches the bottom first? Explain why, sort of thing. Where it could be okay, we have potential energy that turns into rotational plus translational sort of stuff. mgh 1/2 I omega squared plus 1/2 mv squared. I'm going to assume all the m's are the same, and then you go through and figure it out. So basically saying that if we wanted to, it's 2 mgh divided by, what are we dividing by? 2 mgh divided by I over r squared plus m square rooted there. So then you can say, oh, well, in this case, having a bigger I, since I is the denominator, a bigger I means you have a smaller b. And that would be the quantitative portion of that. And then you'd say something like, well, the bigger who, or the bigger moment of inertia is harder to roll, and therefore it takes more energy to get it rolling, and more energy is stored in that rotation. So it should end up with less kinetic energy at the bottom, or linear energy at the bottom, because it's all going through. I can see something like this being a qual-quant sort of thing. I'm not going to expect anything where it's derive the moment of inertia, or even use experimental data to say this is the moment of inertia. I'm expecting to be a whole lot more of what happens if we change the moment of inertia sort of question on there. I can't guarantee it because I didn't write the exam, but that's kind of where I'm seeing it going for this year at least. All right. Any other questions that I can answer before we wrap up today? All right. Then, if you do have any questions or want to shoot me something to think of later, this is my email. Feel free, shoot me a question. You're stuck on a problem, need some help or something like that. Let me know. I'll be glad to at least point you in the right direction. And otherwise, hope to see you guys tonight for some angular rotational stuff, as well as next Wednesday for some practice FRQs with last year's exam. All right, have a great night. Enjoy the rest of your day, and I'll see you guys later.